In 1965, engineer E.A. Johnson created the first capacitive touchscreen, a seemingly science fiction invention that now sits at our fingertips daily. From checking messages before your morning coffee to scrolling social media at bedtime, these screens have become extensions of ourselves. The technology inside your phone screen is creating an invisible electrical field that's constantly detecting changes caused by your conductive body. Let me take you inside the layers of glass, transparent conductors, and insulators that make this everyday magic possible, and explain why your finger works but a pencil eraser doesn't. Have you ever wondered what's really happening beneath that smooth glass surface? The illusion of magic glass. Have you ever stopped to think about what's actually happening when you tap on your phone screen? It seems almost magical. You press your finger against what appears to be just a piece of glass, and somehow your device knows exactly where you touch, what you want to do, and responds instantly. But what's really going on beneath that smooth surface? Your screen is an intricate detection system constantly waiting for your input. Like a spider's web that instantly registers the slightest movement of an insect, your touch screen creates an invisible field that detects your every interaction. When you swipe through a photo album, each subtle movement of your finger triggers precise responses as you navigate from one memory to the next, all without any visible mechanism to explain how this glass surface knows exactly where your finger is moving. Here's something that might surprise you. Your touchscreen isn't actually feeling your finger at all. There's no pressure sensor detecting the physical touch of your skin. Instead, it's responding to something completely invisible, something you can't see, feel, or even sense. Your screen is detecting an electrical property of your body that you carry with you everywhere. It's like a magician's trick. The magician shows you an empty hat, waves a wand, and pulls out a rabbit. You're amazed because you can't see how it happened. Similarly, when you tap your screen, what appears to be simple glass responding to pressure is actually detecting invisible electrical changes in a field you cannot perceive. Once you understand the science of touchscreens, you'll see through this technological illusion. Think about how normalized this interaction has become. Most of us use touchscreens dozens or even hundreds of times every day without giving it a second thought. We tap on our phones to send messages, swipe through photos, pinch to zoom on maps. We use touchscreens at ATMs, in our cars, at restaurant ordering kiosks, and in countless other settings. This technology has become so ubiquitous that we rarely question how it works. Look around at how many touchscreens fill our world. People stand at bus stops, swiping through news articles. Drivers adjust their car's temperature by tapping on dashboard displays. Shoppers check out using touchscreen payment terminals. Children as young as 2 years old intuitively know how to interact with tablets. The technology is everywhere, seamlessly integrated into our daily lives. But when you really think about it, there's something mysterious happening. How could a solid piece of glass possibly detect a human finger through its surface? Glass is an insulator. It doesn't conduct electricity. It's hard and impermeable. Yet somehow it can sense exactly where your finger is even when you're just hovering above the surface. What invisible force could possibly allow this detection to happen? The answer involves an invisible electrical field that exists just above your screen. Every modern touchscreen generates this field, a grid of electrical energy that you can't see or feel, but that's constantly present. And here's where you come in. Your body disrupts this field in a way that can be measured and located precisely. Your body is essentially a walking electrical conductor. The human body contains water with dissolved minerals that allow it to conduct electricity. When you touch a screen, you're creating an electrical connection. Your body absorbs some of the electrical field that the screen generates, and this disruption is what the device actually detects. So how does a piece of glass actually detect your finger? Not through pressure or heat as many people assume, but through electrical disruption. Your screen contains a layer of transparent conductive material, typically indium tin oxide, arranged in a grid pattern. This grid creates an invisible electrical field. When your conductive finger approaches, it disrupts the field in measurable ways. Sensors detect exactly where this disruption occurs, and that's how your device knows where you're touching. The screen itself contains multiple layers, protective glass on top, then transparent conductive layers, insulating layers, and finally the display underneath. The conductive layers create rows and columns that form a grid across the entire screen. When your finger touches a specific location, it changes the electrical capacitance at the intersection of specific rows and columns in this grid. The device's controller chip detects these changes and translates them into screen coordinates. This explains so many things about touchscreen behavior that might have puzzled you. Why don't pencil erasers work on your phone? They're not electrically conductive. Why does water cause your screen to go haywire? Water is conductive and creates multiple contact points. Why can't you use your phone while wearing regular winter gloves? The fabric blocks the electrical connection between your finger and the screen. Before we reveal exactly how modern touchscreens work, let's look at how they used to work. The technology has evolved dramatically over the years, and understanding earlier touchscreen methods helps clarify why today's screens function the way they do. The first widely used touchscreens operated on a completely different principle, one that actually did rely on physical pressure rather than electrical properties. Pressure points, the rise and fall of resistive touch. What if I told you the first touchscreens didn't use electricity at all, but something much more straightforward, pressure? Before your sleek smartphone with its lightning-fast response, touchscreens worked on a completely different principle. These early screens required you to physically press down on the surface until it bent slightly. This technology, called resistive touch, dominated the market for decades before our modern capacitive screens took over. Resistive touchscreens consist of two flexible layers separated by a tiny gap. The top layer is typically made of a scratch-resistant plastic that can bend slightly when pressed. Underneath is another flexible layer, and both have conductive coatings facing each other. When nothing is touching the screen, these layers remain separate, but when you press down, they make contact at the exact point where pressure is applied. This connection creates an electrical circuit, and the device measures where this connection happens. These screens emerged in the 1970s and became the standard for early portable technology. Remember the iconic Palm Pilot? This digital assistant was essentially the Walkman of touchscreen technology, revolutionary for its time but primitive by today's standards. Along with early GPS devices and ATMs of the 1990s, these devices showcased resistive technology that was reliable, relatively inexpensive to manufacture, and reasonably accurate for the era. Resistive touchscreens had significant limitations that became frustrating as technology evolved. They required actual physical pressure. You had to press firmly enough to push the top layer down to contact the bottom layer. This pressure requirement made quick interactions tedious and caused fatigue during extended use. Many people use styluses to apply enough pressure without tiring their fingers. The physical pressure requirement created a slight delay between your action and the device's reaction as the screen deformed. This fraction of a second lag created a disconnected feeling between user and device. The experience felt mechanical rather than intuitive. Accuracy was another major limitation. Resistive screens struggle with precision, especially at edges and corners. The technology could detect a touch in a general area, but pinpointing the exact pixel was challenging. This made detail work frustrating and often required multiple attempts. Perhaps most limiting was the inability to detect multiple touch points simultaneously. Resistive screens recognized only a single point of contact at a time. This meant no pinch to zoom, no multi-finger gestures, and no typing with multiple fingers on virtual keyboards, constraints that seem almost unimaginable now. Despite these drawbacks, resistive screens had one significant advantage. They work with anything. Unlike your current phone, resistive screens responded to any object that could apply pressure: a gloved finger, a pencil eraser, a plastic stylus, or even a pen cap. This universal compatibility made them practical in environments where users might wear gloves like hospitals, factories, or outdoor winter settings. Even today, resistive touchscreens remain in specific applications. Many restaurant kitchen systems use them because they work with greasy fingers or food-safe gloves. Some industrial equipment features resistive screens because they function reliably in harsh environments with dust or moisture. These screens were revolutionary when introduced. Before resistive touchscreens, digital interaction required physical buttons, keyboards, or other mechanical inputs. The ability to touch directly on a screen represented a massive leap forward in human-computer interaction. Users could directly manipulate what they saw without intermediary devices. As mobile technology evolved, the limitations of resistive screens became increasingly problematic. The industry needed a more responsive, accurate solution that could handle multiple inputs simultaneously while requiring less physical effort. The demand for sleeker devices also pushed manufacturers toward alternatives. Resistive screens added bulk due to their layered construction and air gap. The solution came through capacitive touchscreen technology, which fundamentally changed touch detection. Rather than measuring physical pressure, capacitive screens create an electrical field and detect changes when a conductive object approaches. This technology measures electrical properties instead of mechanical force. This shift from mechanical to electrical detection transformed the user experience. Screens could respond to the lightest touch, detect multiple fingers simultaneously, and provide greater accuracy. The technology also allowed for thinner devices since no air gap was required between layers. The trade-off is that capacitive screens only work with conductive objects. Your finger works perfectly because your body conducts electricity, but a plastic stylus or a gloved hand won't register. This limitation was acceptable given the enormous benefits in responsiveness, accuracy, and user experience. Now let's see how modern capacitive screens create an invisible field that your body disrupts. This field exists around your device at all times, silently waiting for your conductive finger to interact with it. Understanding this invisible electrical interaction is key to grasping how your everyday touchscreen actually works. The invisible electric field. Right now, there's an invisible electric field hovering just above your phone screen, and it's constantly waiting for you to disrupt it. This field exists in a perfect state of balance until your finger approaches. Though you can't see, feel, or detect it with any of your senses, this invisible field forms the foundation of how you interact with nearly every modern touchscreen device. Modern capacitive touchscreens operate on a principle fundamentally different from the pressure-based resistive screens we just discussed. Instead of waiting for physical pressure, these screens create an electrostatic field across their entire surface. This field projects slightly above the glass, only about a millimeter or so, but that's enough to detect your finger as it approaches, even before you make physical contact with the screen. This electric field operates silently at such a low power level that it's harmless to the human body. Imagine it as a perfectly calm pond, with the surface tension maintaining a delicate balance. When your finger approaches, it's like a pebble disturbing the water, creating ripples that the system can detect and locate precisely. If we could visualize this electric field, it would appear as a grid of energy flowing across your screen surface. Tiny rivers of electricity run horizontally and vertically, creating a matrix of intersection points covering every millimeter of your screen. These energy pathways form a coordinate system that allows the device to pinpoint exactly where disruption occurs. The creation of this field relies on indium tin oxide, or ITO. This remarkable compound conducts electricity while remaining almost completely transparent. This dual nature makes it perfect for touchscreens where the conductive layer must be invisible. The ITO is applied in microscopically thin layers, typically just a few atoms thick, allowing visible light to pass through almost completely unaffected. These AO layers are arranged in a grid of horizontal and vertical lines on separate layers separated by an insulating material. Each line acts as a separate electrode, carrying a tiny electrical current. The intersections between these lines create nodes where the electric field can be measured independently. A typical capacitive touchscreen consists of multiple layers sandwiched together. From top to bottom, a protective glass or plastic layer that you touch, transparent adhesive bonding disc to the sensors, an ITO layer with horizontal electrodes for X coordinates, a thin insulating layer, another ITO layer with vertical electrodes for Y coordinates, more adhesive and glass separating the touch system from the display, and finally the actual LCD or OLED display generating the images you see. All these layers combined are thinner than a credit card, yet they create a sophisticated detection system tracking your movements with remarkable precision. This layered structure enables the screen to maintain a steady electrical state when untouched, with each electrode carrying a small current and the capacitance at each intersection point remaining constant. The touchscreen controller, a specialized chip connected to all electrodes, continuously monitors these values thousands of times per second. This steady state represents a perfect balance of electrical charge across the entire screen, establishing a baseline against which all disturbances are measured. Consider how this invisible technology saved Lisa during an emergency. While driving through a storm, her car veered off the road. With rain pouring down, her hands wet and shaking, she needed to call for help. Thanks to the capacitive screen's ability to detect her finger through moisture, she could make that critical call without seeing the screen clearly. The invisible field responded to her touch despite the challenging conditions. The physics behind this sensing capability relies on mutual capacitance. Each grid intersection forms a tiny capacitor storing electrical charge. When nothing is near, these capacitors hold a specific charge amount. But when a conductive object approaches, it affects how much charge these capacitors can hold. The controller detects these minute changes and interprets them as touch inputs. Modern touchscreens can detect changes in capacitance caused by a finger hovering just above the surface, enabling features like hover previews on some devices. This sensitivity comes from the uniform capacitive field created by transparent conductors embedded in the screen, forming a grid that generates an electrostatic field extending slightly beyond the physical screen. The system maintains remarkable stability despite environmental changes. Temperature variations, humidity fluctuations, and ambient electrical noise might affect the field slightly, but modern controllers automatically compensate for these factors through continuous recalibration. Only certain materials can disrupt this field. Human skin works perfectly because it's conductive, but many everyday objects have no effect. This selective sensitivity explains why a plastic pen pressed against your phone screen registers nothing. This electrical discrimination allows your device to ignore non-conductive objects while responding instantly to your touch, creating the seamless interaction we've come to expect from modern devices. You are the antenna. Your body is essentially a giant, walking, talking electrical antenna, and that's exactly why your touchscreen responds to you. Every second of every day, your body carries electrical properties that allow it to interact with the world in ways you probably never think about. This electrical nature is precisely what makes modern touchscreens work so well with human fingers. The human body is remarkably conductive to electricity. Though you don't typically think of yourself as an electrical being, your body contains all the necessary components for effective electrical conductivity. The average adult human body consists of approximately 60% water containing dissolved minerals like sodium, potassium, calcium, and magnesium. These minerals exist as ions, atoms with electrical charges suspended in your body's water content. These dissolved minerals transform your body water into an electrolyte solution, similar to sports drinks designed to replace these same minerals when you sweat. This creates a conduction highway throughout your body, enabling electrical interactions. Your cells, tissues, and skin readily interact with electrical fields because of this unique composition. Imagine walking through a crowded mall. As you pass electronic devices, your body silently broadcasts its electrical presence. The store security gates detect your approach, automatic doors sense your arrival, and your smartphone responds instantly to your touch. All this happens because you're essentially a mobile electrical entity, though you can't see, feel, or hear this aspect of your physiology. The human body both stores and conducts electricity. Your skin, particularly the epidermis, acts as a capacitor that stores electrical charge. Meanwhile, your body fluids serve as conductors, allowing electrical current to flow through you. This dual nature makes your body electrically unique compared to most objects in your environment. A simple demonstration shows this conductivity clearly. Touch both ends of a basic electrical circuit containing a small LED light and a battery, and the LED illuminates. Your body completes the circuit by providing a path for electrical current. The electricity doesn't harm you because the current is very small, but it's enough to light the LED. The same principle enables touchscreens to detect your finger. Your finger effectively interacts with touchscreens because of its high concentration of conductive fluids near the skin surface. The fingertip contains numerous sweat glands, creating a moist environment rich in electrolytes. Even when your fingers feel dry, they contain enough moisture and minerals to conduct electricity efficiently. When your finger approaches a touchscreen, it becomes an extension of the screen's electrical field. When your finger nears a capacitive touchscreen, something fascinating happens microscopically. The screen's electric field extends slightly beyond the glass, creating an invisible detection zone. As your conductive finger enters this zone, it absorbs some electrical charge from the screen's field. This absorption occurs most strongly at the exact point where your finger touches the screen. From the screen's perspective, your finger appears as an electrical anomaly, a conductive object distorted in the uniform electric field. Your finger essentially steals electrical charge that would normally remain in the screen's capacitive grid. This creates a measurable drop in capacitance at specific points on the screen. The screen's controller chip detects this localized capacitance drop and calculates precisely where your finger is positioned. It accomplishes this by measuring changes across the entire sensor grid embedded in the screen, creating a map of decreased capacitance. The center of this disturbance pattern corresponds exactly to your finger position. Modern touchscreens contain sensing grids with hundreds or thousands of intersection points, allowing sub-millimeter accuracy. The controller can detect subtle changes as your finger moves, tracking the changing pattern of electrical disruption to follow your gestures smoothly. Your entire body acts as an electrical ground in this interaction. When your finger absorbs charge from the screen, that charge disperses throughout your body rather than building up in your fingertip. This grounding effect is crucial for touch detection. If your finger were electrically isolated from your body, the detection wouldn't work properly because the charge couldn't dissipate. This explains why other conductive objects sometimes work on touchscreens. Metal styluses work because metal conducts electricity well. Fruits with high water content like bananas can trigger touchscreens because they contain similar electrolyte solutions. Even some animals can operate touchscreens because their bodies share the same conductive properties as humans. Each time you tap on your phone screen, you participate in an invisible electrical exchange. Your body absorbs tiny amounts of charge, creating disturbances in the screen's electric field that the device interprets as intentional touches. This electrical conversation happens constantly, with your body and device exchanging information through electrical conductivity. Now let's see what actually happens in that crucial moment when your finger touches the screen. The instant your skin makes contact with the glass surface, a complex chain of electrical events begins. A precisely engineered detection system springs into action to register your touch, the moment of contact. What exactly happens in that split second when your finger touches the screen? A complex electrical dance begins. This moment, the instant your skin makes contact with the glass, triggers a cascade of events that happen faster than you can blink. While it seems like a simple tap to you, your phone sees it as an electrical disruption that must be precisely measured, located, and interpreted. Let's slow down time and watch what happens when your finger approaches the screen. Before you even make contact, your finger enters the invisible electric field that hovers just above the glass surface. Your conductive skin begins to interact with this field when you're still a millimeter or two away. The field bends slightly towards your finger, drawn to its conductive properties. This slight distortion creates the first hint of electrical change the screen can detect. As your finger moves closer, the distortion grows stronger. The electric field, which normally flows in a stable pattern across the screen, starts to warp more dramatically around your approaching digit. Think of it like a magnetic field bending around a piece of metal. Your conductive finger pulls and distorts the electrical energy in its vicinity. When your fingertip touches the glass, your body forms an electrical connection with the screen sensing system. Your finger creates a capacitive coupling with the screen's electrodes. Capacitance is a fundamental electrical property, the ability of a system to store electrical charge. The screen sensing grid consists of tiny capacitors at each intersection point. When your finger touches near these intersections, it changes how these capacitors function. Your conductive body becomes part of the electrical system, creating a new path for the electric field to flow. The electrical changes involved are measured in picofarads, 1/1,000,000th of a farad. Imagine a high-speed camera capturing water droplets in ultra-slow motion, revealing ripples and splashes invisible to the naked eye. Similarly, the touch controller chip captures these minuscule electrical disruptions with extraordinary precision, thousands of times per second. The controller constantly scans the entire grid of sensors embedded in your screen. When your finger touches the screen, it detects the drop in capacitance at specific points. Your fingertip affects multiple sensor intersections simultaneously, creating a pattern of disturbance resembling a small hill or dome, with the greatest change at the center and smaller changes in the surrounding area. How does your device respond so quickly despite the complex electrical calculations involved? The controller analyzes this pattern using sophisticated algorithms, calculating the precise center point of the disturbance pattern with sub-millimeter accuracy. This entire process from touch to location calculation happens in under 10 milliseconds, faster than your nervous system can process sensory information, which is why touch screens feel instantaneous. Your entire body serves as an electrical ground in this system. The tiny amount of charge that your finger absorbs disperses throughout your body. This grounding effect is essential for the capacitive detection to work properly. If your finger were somehow electrically isolated, the touch detection would be much less effective. The precision involved is remarkable considering the environmental challenges. Your screen must measure these tiny electrical changes accurately despite electrical noise from other components, interference from nearby devices, and even temperature variations. Through sophisticated signal processing, the touch controller maintains reliable detection. After determining your finger's exact location, the touch controller translates this physical touch into a digital action. The touch location converts the specific X and Y screen coordinates that are sent to your phone's operating system, which determines what should happen based on what's displayed on screen. For complex gestures like swiping or pinching, the touch controller builds on the same electrical principles. It tracks the change in pattern of capacitance over time. For a swipe, it records a series of touch points as your finger moves across the screen. For pinching, it simultaneously tracks two separate touch patterns and measures how the distance between them changes. The system's ability to detect these nuanced movements stems directly from its capacity to track the electrical disruptions your fingers create moment by moment. So when your finger touches the screen, your conductive finger absorbs some electrical charge, creating a measurable drop in capacitance that sensors detect and locate precisely. The controller chip measures these electrical changes thousands of times per second, translating physical touches into digital commands that control everything your device does. But if it's all about conductivity, why don't other objects work on your touch screen? If your phone is detecting electrical disruptions, shouldn't any object disrupt the field? The answer reveals an important distinction between materials that helps explain some of the most common touchscreen frustrations. Why your pencil doesn't work. Ever tried tapping your screen with a pencil or while wearing winter gloves? The screen completely ignores you. But why? You push harder, tap repeatedly, try different angles, but nothing happens. Meanwhile, the lightest touch from your bare finger registers instantly. This seemingly mysterious behavior actually reveals a fundamental principle about how modern touchscreens work. Your touchscreen responds to electrical conductivity, not physical pressure. This creates a fundamental division in our world. Objects that conduct electricity and those that don't. Like a door that only opens with specific keys, your touchscreen only recognizes that can carry an electrical current. Conductors allow electricity to flow through them easily. Your body conducts electricity because of the water and minerals inside you. Metals like aluminum, copper, and stainless steel also conduct electricity. These materials contain free electrons that move easily, creating pathways for electrical current. When these materials touch your screen, they absorb some of the electrical field, registering as a touch. Insulators resist electrical flow. Materials like plastic, wood, rubber, and standard fabric fall into this category. Their electrons remain tightly bound to atoms, preventing electrical current from flowing. When you touch your screen with an insulator, the electrical field remains stable and undisturbed. Your phone detects nothing. This explains why everyday objects fail on touchscreens. A wooden pencil doesn't register because wood insulates electricity. The eraser end fails too, since rubber also insulates. Plastic pens, paper corners, chopsticks, shirt sleeves, all insulators your screen cannot detect. You can easily demonstrate this principle. Tap your phone with a plastic pen and nothing happens. Now touch the screen while holding the pen. The screen responds because it detects your conductive finger, not the pen. The screen specifically requires conductivity to function. This principle explains one of winter's most frustrating technology problems. When temperatures drop and you're standing at a bus stop, trying to check arrival times, your gloved fingers can't operate your phone. The fabric or leather acts as an insulator, blocking the electrical connection between your finger and the screen. Even thin gloves cause this problem because material composition matters more than thickness. The screen detects electrical interaction, which the insulating glove prevents. Some materials fall between conductors and insulators. These semiconductors, like silicon and computer chips, have intermediate electrical properties. They typically don't work well on touchscreens unless specifically designed for that purpose. Other slightly conductive materials might register occasionally but not reliably, explaining why some objects work unpredictably. Humidity sometimes changes how materials interact with touchscreens. On very humid days, moisture collects on surfaces, creating a thin water film. Since water conducts electricity, this moisture sometimes allows otherwise non-conductive materials to register touches. A wooden pencil might occasionally work in humid environments because the moisture gets detected, not the wood itself. Understanding this conductor-insulator distinction explains specialized touchscreen accessories. Touchscreen styluses have conductive tips specifically designed to mimic your finger's electrical properties. Most contain conductive rubber or fabric infused with conductive particles that create the same electrical disturbance your finger would. Stylus technologies evolved significantly. Early versions had large, soft, conductive rubber tips that worked but lacked precision. Modern styluses incorporate sophisticated conductive materials. and sometimes active electronic components generating weak electrical signals to enhance detection. Premium styluses communicate wirelessly with devices to improve accuracy and add features like pressure sensitivity. Touchscreen-compatible gloves solve the winter dilemma through material engineering. These gloves incorporate conductive threads, usually containing silver or copper, woven into the fingertips. These metallic threads create an electrical pathway from your finger through the glove to the screen. When wearing these gloves, the conductive threads allow your body's electrical properties to interact with the screen's electric field, registering touches correctly. These conductive threads often appear as different colored stitching in the fingertips. Some manufacturers use conductive particles embedded throughout the fabric instead, but the principle remains the same, creating an electrical connection between your body and the screen. DIY enthusiasts have found creative solutions too. Some modify regular gloves by sewing conductive thread into fingertips. Others apply conductive paint or attach small conductive pads. There are even conductive sprays that temporarily make non-conductive materials work with touchscreens. So how do capacitive touchscreens distinguish between fingers and other objects? They detect whether the object conducts electricity. Fingers do, while insulators like plastic and regular fabric don't. The screen's electric field remains undisturbed when touched by non-conductive materials, but conductive objects create measurable changes interpreted as touches. Speaking of things that confuse touchscreens, let's talk about their biggest enemy, water. While human fingers work perfectly under normal conditions, introduce a few droplets of water, and suddenly your touchscreen goes haywire, registering phantom touches and ignoring your actual finger. When water confuses your screen, have you noticed how your phone goes haywire when your screen is wet or your fingers are damp? There's a fascinating electrical reason for this chaos. Water and touchscreens have a complicated relationship that causes some truly bizarre behavior. This seemingly simple liquid creates one of the most frustrating problems for touchscreen users worldwide. Water presents a unique challenge for touchscreens because it's electrically conductive like your finger. The water we encounter in daily life contains dissolved minerals that enable conductivity. Rain, tap water, sweat, and even the moisture from your breath contain enough minerals to conduct electricity, allowing water to interact with your touchscreen's electric field similarly to your finger. You might expect water to work predictably on touchscreens given its conductivity. Instead, water causes erratic behavior. Your screen registers phantom touches in random locations, ignores your actual finger, launches apps, types gibberish, or scrolls wildly through content without you touching anything. The screen behaves erratically until you thoroughly dry it off. Imagine you're caught in a sudden downpour, desperately trying to text someone that you'll be late. As raindrops hit your screen, your message transforms into a jumble of random characters. The keyboard seems possessed, selecting letters you never touched while ignoring your actual taps. Your carefully typed message becomes digital nonsense, all because tiny droplets are creating electrical mayhem. This chaotic response occurs because water behaves differently than your finger on a touchscreen. When a water droplet lands on your screen, it spreads unpredictably across the surface. Each droplet creates a constantly changing shape as surface tension battles with gravity in the screen's properties. The droplet might form a circle, an irregular blob, or split into multiple smaller droplets. These water droplets essentially become miniature storm clouds on your screen's surface, creating electrical disturbances across multiple sensors simultaneously. Unlike your finger, which creates a single, well-defined area of electrical interaction, water bridges multiple sensors across different areas. A single droplet connects points that would normally be independent, creating electrical pathways between distant locations on the sensor grid. Your phone's touch detection system isn't designed for this complex multi-point contact. The screen controller chip expects touches to follow certain patterns, single points for taps, smooth lines for swipes, or a few distinct points for multi-finger gestures. Water violates these expectations by creating irregular, constantly changing patterns across multiple sensors. When water bridges multiple sensors, the touch controller becomes confused. The controller tries to interpret electrical signals coming from dozens of points simultaneously, all with varying intensities as the water shifts. From the controller's perspective, this might look like several fingers touching at once or a finger dragging erratically. The system interprets these signals according to its programming, triggering random actions. The problem worsens when using your finger on a wet screen. The controller must distinguish between water's conductivity and your finger's conductivity, both creating electrical disturbances. Often, water creates so much electrical noise that your intentional touches get lost in the chaos. The controller can't isolate your touch from the background noise created by water droplets. Water droplets also change shape when you touch the screen. Pressing on a screen with water droplets causes them to spread unpredictably, creating new electrical pathways in real time. A single finger press might register as a complex pattern of touches as water redistributes across the screen surface. Newer smartphones implement sophisticated water rejection algorithms to address this problem. These systems use advanced signal processing to distinguish between finger touches and electrical noise from water droplets. The algorithms identify characteristics typical of water, like multiple simultaneous contact points that change rapidly in irregular patterns. Some devices use hardware solutions to reduce water sensitivity, adjusting the electrical properties of the sensing system or incorporating hydrophobic coatings that cause water to bead rather than spread, reducing the chance of droplets bridging multiple sensors. The most advanced water rejection systems combine multiple approaches, using machine learning algorithms trained on thousands of examples of both finger touches and water droplets. These systems recognize water's electrical signatures and filter them out, allowing finger touches to be detected even on wet screens. Water remains one of touchscreen technology's biggest challenges because it's conductive enough to trigger the screen, but behaves electrically unlike a human finger. The next time your phone behaves strangely in rain or with damp hands, you're witnessing complex electrical interactions that confuse even sophisticated modern devices. Now that we understand the basics, let's look at the hidden layers inside your screen that make all this possible. The seemingly simple glass surface conceals a sophisticated stack of materials working together to detect your touch. Inside your screen, the hidden layers. If we could peel back the glass of your smartphone, you'd see a marvel of engineering with multiple invisible layers working together. Your screen isn't just a single piece of glass. It's a sophisticated sandwich of specialized materials, each performing a specific function. This complex structure hides in plain sight. The layers are so transparent you never notice them while using your device. What appears to be simple glass on your phone is actually a technological wonder containing at least 6 distinct layers. Each layer maintains almost perfect transparency while performing complex electrical functions, creating a remarkable engineering challenge where materials must conduct electricity, sense touch, and display vibrant images while remaining invisible to users. The outermost layer you actually touch is called the cover glass or cover lens. This protective layer is engineered to be extremely durable, typically made from specially formulated glass like Corning's Gorilla Glass. This specialized glass undergoes ion exchange processes where larger ions are stuffed into the glass structure, creating a compressed surface that resists scratches and cracks. The cover glass also has oleophobic coatings that resist fingerprints and make the surface smoother for your finger. Beneath this protective layer sits the touch sensor assembly where touch detection happens. The touch sensor consists of multiple sublayers that work together to create an electric field. The most critical component is a grid of transparent conductive material, typically indium tin oxide, ITO. ITO is a fascinating material that manages to be both electrically conductive and optically transparent, properties rarely found together in nature. Most conductive materials like metals are opaque, while most transparent materials like glass are insulators. ITO bridges this gap, allowing electrical pathways to exist in something you can see through. The touch sensor arranges this ITO material in a precise grid pattern, extremely thin wires thousands of times thinner than a human hair, arranged in rows and columns. These rows and columns are separated by a thin insulating layer, with each crossing point forming a tiny capacitor that detects changes in the electric field. Manufacturing these layers presents enormous challenges. The ITO must be applied in layers just nanometers thick using sophisticated vacuum deposition techniques. For perspective, a single dust particle landing on the substrate during manufacturing can create a permanent dead spot on the screen. This is why these components are produced in clean rooms where the air contains fewer than 100 particles per cubic foot, about 1,000 times cleaner than hospital operating rooms. Beneath the touch sensor lies the display itself, typically OLED or LCD technology. This layer creates all the images you see, with millions of individually controllable pixels generating light and color. The display must work in perfect harmony with the touch sensor. Any misalignment would make touches register incorrectly. Between these major components sit additional specialized layers, polarizer films controlling light passage, optical adhesives bonding layers together, and thin film transistors forming the electronic backbone controlling individual pixels. All these layers connect to a specialized controller chip, typically located at the edge of the screen. This touch controller is a purpose-built microprocessor dedicated to touch detection. It connects to the ITO grid through thin, flexible circuits and constantly measures the electrical properties at each intersection point. The controller samples the entire grid thousands of times per second, checking for capacitance changes, indicating finger touches. It can detect changes as small as a fraction of a picofarad while filtering out electrical noise from the phone's components, nearby electronics, power lines, and atmospheric electricity. Modern controllers can track 10 or more fingers simultaneously, measure pressure intensity, and even detect hovering fingers. Some recognize the unique electrical signature of water droplets and ignore them to prevent false inputs. Manufacturers add additional components for specific features. Fingerprint sensors under the display include specialized optical or ultrasonic sensors. Devices with stylus support contain extra sensing grids, and phones with variable refresh rates include additional control circuitry. All these components work together flawlessly while remaining completely invisible. When functioning properly, you never think about the complex technology sandwiched beneath your fingertips. You simply touch the screen and the phone responds, creating the illusion of direct manipulation of digital objects. What are the hidden layers inside your smartphone screen? A sophisticated stack including protective glass, transparent conductive grids, insulating layers, and a display, all controlled by specialized chips. This technological marvel combines advances in materials science, electrical engineering, manufacturing precision, and computing power to create the seamless touch experience we now take for granted. With this touch innovation, special gloves and beyond. Ever wonder how some gloves work with touchscreens while others don't? The answer reveals the clever ways we're adapting to this technology. Winter brings a familiar frustration, having to remove your gloves to use your phone, exposing your hands to freezing temperatures just to send the text or check directions. This problem has sparked an entire industry of touchscreen-compatible gloves that solve this electrical disconnection while keeping your hands warm. These specialized gloves face a challenging design problem. Regular winter gloves are specifically made to insulate, to create a barrier between your skin and the outside world. But this insulation blocks the electrical connection that touchscreens require to function. Touchscreen-compatible gloves maintain warmth while creating an electrical pathway between your finger and the screen. I remember standing at a bus stop one winter morning, frantically trying to check my arrival time while my fingers turned numb from the cold. Every few seconds I removed my glove, tapped the screen, then quickly covered my freezing hand again. That frustrating experience made me appreciate the ingenuity behind touchscreen gloves when I finally got a pair. The most common solution involves conductive threads woven into the fingertips. These threads typically contain silver or copper, embedded within the fabric. When you touch your screen while wearing these gloves, the conductive threads act like tiny bridges, allowing your body's natural conductivity to flow through and interact with the screen's electric field. If you look closely at touchscreen gloves, you can often see these special threads. They frequently appear as slightly different color stitching in the fingertips, sometimes forming patterns like X-shapes or spirals. This patterning ensures consistent electrical contact regardless of which part of your fingertip touches the screen. Some manufacturers hide these threads within the fabric to maintain a more uniform appearance. The materials used vary widely. Some use actual metal fibers, extremely thin strands of silver or copper woven among the regular fabric threads. Others use synthetic fibers coated with metallic particles or conductive polymers. All aim to create enough conductivity while maintaining flexibility, comfort, and durability. Beneath the outer fabric layer, these conductive threads concentrate primarily in the fingertips. They run from the outside surface where you touch the screen inward towards your finger, creating a complete electrical path. In higher quality gloves, these conductive elements extend further into the palm area to ensure better conductivity with your skin. The technology continues to evolve with different approaches. Some manufacturers use conductive leather or fabric panels on the fingertips rather than threads. Others incorporate conductive particles throughout the entire glove material. Advanced versions use multiple conductive layers to improve reliability and touchscreen response accuracy. When using these gloves, you're extending your body's natural conductivity through the material. Your finger remains the source of the electrical interaction. The glove merely creates a pathway for this electrical property. Without your conductive body inside them, these gloves wouldn't work on a touchscreen at all. This solution represents a clever application of understanding touchscreen science. By recognizing that screens detect electrical conductivity rather than pressure, engineers modified gloves to become electrically conductive while maintaining their warming properties. Beyond gloves, a similar approach applies to touchscreen styluses. The first generation simply mimicked your finger's electrical properties with conductive rubber or foam tips. These passive styluses transfer your body's conductivity through the stylus to the screen, which is why they typically have metal bodies that you must touch while using them. More advanced active styluses generate their own weak electrical signals. These battery-powered devices create specific electrical frequencies that touchscreens recognize, allowing for greater precision in features like pressure sensitivity and palm rejection. The Apple Pencil, Samsung's Pen, and Microsoft's Surface Pen all use variations of this active technology. Some companies have developed conductive fabrics that can be sewn into any glove, allowing people to convert their favorite existing gloves into touchscreen-compatible ones. Others created removable fingertip covers or conductive sprays and liquids that can be applied to normal gloves. For industrial environments, manufacturers have developed composite gloves with conductive materials strategically placed only at the fingertips, maintaining necessary safety properties while adding touchscreen functionality for workers operating digital equipment in harsh conditions. The success of touchscreen gloves highlights our relationship with digital technology. Rather than adapting our devices to work with existing gloves, we've modified our gloves to work with our devices. This pattern repeats throughout technology history, human adaptation to technological constraints. Looking to the future, touchscreen technology continues evolving. While we've adapted our accessories to work with current touchscreen limitations, emerging technologies may change how we interact with our devices, potentially making special gloves unnecessary or enabling entirely new forms of interaction that don't involve physical contact at all. The future, beyond the touch. What if you could control your screen without even touching it? The next generation of touch technology might eliminate contact altogether. Engineers and researchers are developing systems that can sense your intentions before your finger ever reaches the glass. These technologies represent completely new approaches to how we interact with our digital devices. Several major technology companies are exploring interaction systems that work without physical contact. Samsung has implemented limited hover detection in some devices, allowing screens to sense when your finger is hovering above certain elements. Apple has filed multiple patents for non-contact sensing technologies. Google's Project Solly developed radar-based hand tracking that detects tiny finger movements in the air. These companies are investing billions because moving beyond physical touch creates new possibilities for human-computer interaction. Hover detection represents the immediate evolution of current touchscreen technology. These systems extend the sensing range of the capacitive field above the screen surface. While standard touchscreens detect your finger about a millimeter away, advanced hover detection can sense it from several centimeters. This extended range allows the screen to know your finger is approaching before contact occurs. This pre-contact awareness enables new interface possibilities. Imagine hovering over an icon and seeing it expand with additional information before touching it. Or picture a drawing app showing a preview of your brushstroke as you position your finger above the canvas. These hover interactions create an additional dimension of control beyond touches and swipes. The technology builds on existing capacitive systems, but requires more sensitive measurement capabilities. The electrical field changes from a hovering finger are smaller than those from direct contact. Detecting these subtle changes requires sophisticated sensors and processing algorithms. The screen must also distinguish between intentional hover gestures and hands simply passing over the device. Predictive touch systems attempt to anticipate where you'll touch before contact. These systems analyze hand movement trajectory to predict your intended target. By the time your finger reaches the screen and the device is already prepared for the interaction, reducing response time and potentially selecting targets even if your touch isn't perfectly precise. Jaguar Land Rover has developed a predictive touch system for vehicle dashboards that reduces driver distraction by up to 50%. The system tracks hand movements and predicts which control the driver intends to use. Similar technology could help people with hand tremors interact more effectively with touchscreens by inferring their intended targets despite imprecise movements. Mid-air gesture control systems, like waving a magic wand in the air, detect hand movements without requiring device contact. Using cameras, infrared sensors, or radar, they track hand position and gestures in three-dimensional space. You can swipe through photos, adjust volume, or answer calls with simple movements above or beside your device. Microsoft's HoloLens uses this approach for augmented reality control. Google's projects solely miniaturized radar technology to detect subtle finger movements, allowing users to perform precise controls like turning an invisible dial between thumb and forefinger. These technologies create a spatial interaction zone around your device rather than limiting control to the physical screen. The challenges include distinguishing intentional gestures from casual movements and providing clear feedback. Without the physical sensation of touching a surface, users need visual or audio cues to confirm their actions. Systems must work reliably in different lighting conditions and environments. Equally important innovations are happening in output, how devices provide feedback. Current touchscreens are essentially flat glass that provides no tactile feedback. Advanced haptic technologies aim to create the sensation of texture and physical response on flat surfaces. Systems like Canvas Touch can make areas of the screen feel rough, smooth, bumpy, or sticky without moving parts, using electrostatic fields to modulate friction between finger and screen. Other approaches use ultrasonic vibrations to create localized sensations under your fingertip, simulating buttons clicking or switches toggling. Some experimental systems can even create the sensation of 3D objects rising from a flat screen. These emerging technologies might transform our understanding of what a touchscreen actually is. Future interfaces might exist as interaction zones where hand positions, gestures, eye movements, and even brain activity combine to create seamless control. The glass screen might become just one component in a multi-sensory interface system extending into the space around the device. What if future devices could read our intentions without any movement at all? Technologies like hover detection, predictive touch, mid-air gestures, and advanced haptics are moving us toward interfaces that blend physical and digital worlds more seamlessly, responding to our intentions with less explicit input required. Through the evolution from pressure-sensitive resistive screens to electrically sensitive capacitive technology, and now toward non-contact systems, we can trace a trajectory of increasing abstraction. Each generation moves further from mechanical interaction toward detecting the user's intentions more directly. Will our future devices eventually respond directly to our thoughts rather than physical movements? Extreme touchscreens when the rules change. How do touchscreens work in freezing Arctic temperatures or inside industrial furnaces? The answer reveals the remarkable adaptability of this technology. Your everyday smartphone touchscreen operates within a narrow range of conditions. It expects a room temperature environment and the touch of a bare human finger. But what happens when these ideal conditions can't be met? In extreme environments, standard capacitive touchscreens simply fail, creating a serious problem for industries that need reliable touch interfaces in challenging settings. Imagine an oil worker on an Arctic drilling platform operating digital equipment while wearing thick insulated gloves in temperatures reaching minus 40 degrees Fahrenheit. Or picture a factory technician controlling a touchscreen interface inside a glass manufacturing facility where ambient temperatures exceed 150 degrees Fahrenheit. Standard consumer touchscreens become completely unusable. Arctic cold makes capacitive screens unresponsive, while extreme heat causes sensor distortions and damages internal components. These challenges have pushed engineers to develop specialized solutions, the tough superheroes of the touchscreen world. Like superheroes with unique powers, each technology variant tackles specific environmental villains. Military equipment showcases some of the best examples of this ruggedized technology. Military-grade tablets and control systems function in deserts, jungles, Arctic conditions, and even underwater. These devices use reinforced glass that withstands impact, pressure changes, and temperature extremes without cracking. Their internal components operate in temperature ranges from minus 40 degrees Fahrenheit to 160 degrees Fahrenheit, far beyond consumer device capabilities. When capacitive touch technology fails, alternative detection methods take over. Infrared touch systems create an invisible grid of light beams across the screen surface. When touched, your finger breaks these beams at specific points, allowing the system to determine location. Unlike capacitive screens, infrared systems don't rely on electrical properties, so they work with gloves or non-conductive objects in temperatures where capacitive systems would fail. Surface acoustic waves, SAW technology, uses ultrasonic waves traveling across the screen. When touched, your finger absorbs acoustic energy, creating detectable changes in the wave pattern. These systems operate in extreme temperatures and work with gloved hands, though heavy vibration or contamination can affect performance. For the harshest industrial environments, resistive touchscreens make a comeback. While largely abandoned in consumer devices, resistive screens thrive in factories, industrial kitchens, and outdoor settings. Their mechanical operation makes them reliable in extreme conditions, working with any pressure-applying object, ideal for environments requiring heavy protective gear. Consider offshore oil platforms in the North Sea, where workers must monitor critical systems in harsh conditions. Traditional interfaces would fail, but specialized touchscreens with infrared technology allow operators to maintain precise control even while wearing thick insulated gloves. During a recent storm, when temperatures plummeted and sea spray-coated equipment, these ruggedized interfaces continue functioning, preventing potential equipment failures worth millions. Industrial touchscreens operate with barriers between finger and screen. Some detect touches through gloves up to half an inch thick or function when covered with protective overlays. This capability proves crucial where direct skin contact would be impractical or unsafe. Beyond temperature, challenges include vibration, moisture, and contaminants. Construction equipment and military vehicle screens incorporate vibration dampening systems that filter out false inputs from equipment movement. Marine application screens use additional sealing and specialized algorithms distinguishing between water droplets and intentional touches. Waterproof touchscreens represent impressive engineering achievements. Truly waterproof screens operate while completely submerged, using fully sealed housings and specialized detection systems that function when covered with water. Underwater tablets used by marine researchers and offshore workers provide digital interfaces in environments that destroy conventional electronics. Clean rooms and sterile environments present unique challenges. These screens function perfectly while being repeatedly sterilized with harsh chemicals, something that would degrade standard touchscreens. They use specialized glass formulations and sealants resisting chemical attack while maintaining optical clarity and touch sensitivity. Medical-grade touchscreens incorporate antimicrobial materials preventing bacteria growth. Manufacturers must consider human factors in their designs. Workers in challenging environments may have limited dexterity due to protective gear or may experience physical stress from environmental conditions. This drives design choices like larger touch targets, simplified interfaces, and confirmation mechanisms preventing accidental activation. These specialized touchscreens demonstrate how engineers adapt core technologies to meet specific challenges. Rather than forcing users to accommodate technological limitations, these systems are engineered to function where needed most. This adaptability has allowed touchscreen interfaces to spread into virtually every industry, creating a universal interaction method across an incredible range of conditions. Now that we've seen the full spectrum of touch technology, let's wrap up what we've learned about the science behind this everyday wonder that connects us to our digital world. The next time you tap on your phone screen, remember what's really happening. Your finger disrupts an invisible electrical field that extends just above the surface. Your body, a natural electrical conductor, absorbs some of this field, creating a disturbance that tiny sensors detect and locate with incredible precision. This interaction represents a complex fusion of physics, materials science, and electrical engineering working together to create the seamless experience we take for granted. Touchscreens have transformed how we connect with technology and each other. What other technologies do you use daily without understanding their